terms of our impact in the UK, it made it to the UK again, collected it in the rainwater. You can see examples from here. You can see the ash grains themselves are really nice. You can see the outlines of the bubbles that the pumice was made of. You can see where it was collected, mainly rainwater samples in the north of the UK. We also looked at pollen sensors, and you can see that actually it was found across the UK when you take that into account. This was work that was done in association with the Met Office and the British Geological Survey. The Scottish Environment Protection Agency were also looking at the chemistry of rainwater, and what they found was when you take samples from the north of Scotland and you measure the iron content, then they could find that the iron content was much higher up there. And these people definitely got noticeable amounts of ash this time. So if you were anywhere up here, for example, if you were in Thurso, then you're seeing your car is noticeably dirty, noticeably covered in ash. So we definitely got a good hit from Grimsby. You could also track it using air quality monitoring equipment. So you might have heard DEFRA or seen some data from DEFRA's network during the last few weeks when the air pollution was bad. And this is a graph of PM10, which is particles less than 10 microns in the atmosphere. The grey parts represent man-made particles, and the blue is the total. And so what you can see is we've got a big spike here. This is on the 24th of May. And that big spike has no relationship to man-made particles. So this is the ash cloud coming across the country. This example here was from Leeds. If you look at all the places where we got it, you can see that all of the northern part of the country is there. The size of the circle is proportional to the dose, so actually Aberdeen got the most, although we don't have any sensors further north. And then the other thing that was pretty cool about these data is that we know the times of the spikes, and so that's what the color coding is on these dots, and so you can actually see that the plume started in the north and made its way south and got as far as the Midlands. So you can track that in the air quality data. You can see the plume coming across. One other thing that was pretty cool, this was work that we did with the British Geological Survey, is we managed to get citizen scientists. So we got volunteers, we got lots of people from primary schools and lots of geography teachers to help us, and they sent in tape samples to us. So this video here, there's a video we put on YouTube. This is my wife doing a Blue Peter thing. She's showing how you can take some sellotape and you can put it outside with the sticky side up. You can leave it there for a while, then you can put a piece of paper on it, write the details, your postcode and stuff, send it into the British Geological Survey, and then we look through them to work out which ones had ash in them. Pretty tricky to tell. The ash particles are really small and the microscopes you can use aren't too powerful, but you get a pretty good idea. You can recognize them because they're kind of glassy and brown, and sometimes you can see the way they clump together. But you also get people sending in stuff that's definitely not ash. So there's wind-blown sand from around here, and if you live somewhere near Hartlepool or in the northeast, then I don't know what you're breathing, but this looks like soot or some kind of industrial gunk that seemed to be in a lot of those samples. And then we've just got general dead flies and things like that. But these data turned out to be really useful. And when you plot up a map of where we were sure we had it, then it's basically only Scotland. And the places where we thought we had it, that's mainly in the north. And the result of this video meant that everyone also told us the time that their samples were out. So if you plot a graph of latitude versus time, you can see where all the samples overlap. And if you look at where they all overlap on May the 24th, which is what we saw in the air quality and in all the other data as well. So this was something that worked really well, and I think we definitely want to do this again in the future. And in fact, the British Geological Survey have just released an app called My Volcano. You can get that in the App Store, and that contains information about different volcanoes around the world, and also contains instructions so that you can collect samples if we have another eruption sometime soon. Okay. So one of the things around the time of the Eyjafjallajökull eruption that people said was, well, why has this never happened before? Like, surely Iceland's been having volcanoes have been erupting for ages. Why have we not had this happen before? And basically, you can kind of see the reasons for it when you have a little look into the history of ash clouds and aviation. So the top graph here is basically showing all the times since the end of the Second World War when there's been a volcano erupting in Iceland. You can see that actually happens fairly often. And had times of nearly constant activity, for example, Surrey in the 60s and the Krapla fire in the 80s. So those eruptions go on quite a lot. But most of those eruptions are basalt, and most of them haven't produced much ash. So in fact, the only eruptions that produce much ash are the ones that I've marked on here: Hekla 1947, Eyjafjallajökull, and Grimsby. And so that is really instructive when you compare that to a graph of how global air traffic has developed over the past 50 years. When you look at it, it's done this. So back when Hecla erupted in 1947, you couldn't even get a passenger jet across the Atlantic. And in that time, as the traffic's grown, and here when Concorde's launched, there's still not been a decent sized eruption. And it's not until global traffic's got high enough that we start to get planes interacting with volcanoes that people start to realize that this is a problem. So the two examples we've got here, BA Flight 9 and KLM Flight 867, these are planes that went into ash clouds in Indonesia and in Alaska, and they had all their jet engines shut down, and the planes started to come down, and luckily in both cases they were able to restart the engines and they were able to land safely. But these were the times when people were realizing, right, well actually these volcanoes, we need to start worrying about these. So they set up a network of volcanic ash advisory centers, and they basically came up with the advice that an airplane should avoid all ash. So these were the rules that happened when Eyjafjallajökull erupted. And if you remember looking at the places where ash was detected in Eyjafjallajökull, if you make that avoid all ash, then it's no wonder that most of European airspace was shut down. And actually what happened during the Eyjafjallajökull eruption was people saw this was going on, they saw that this was a crisis, and they actually loosened the rules a little bit so that planes can now fly in a little bit of ash. And that actually happened during the Eyjafjallajökull eruption, and that was the state of the rules during the Grimsby eruption. So the Grimsby eruption took place during different rules to the Eyjafjallajökull one. And you can actually see that that makes quite a difference. So this is a chart made by the Met Office Volcanic Ash Advisory Center. And under the new rules, you can fly through the blue stuff, but you can only fly through the gray if you have special permission, and you pretty much can't fly through the red. So these are the rules that we've got then. And that means you can see here that there's lots of areas that are blocked out, but compared to during the Eyjafjallajökull eruption, during Eyjafjallajökull, you couldn't fly through any of the colored zones. So with the Eyjafjallajökull rules, then there's a colored zone that swoops here over across the southern part of the UK. So that means that if they'd had the same rules during the Grimsby eruption, then it would have gone right across London. That means Heathrow's shut, it means Gatwick's shut, it means that Paris Charles de Gaulle's shut, and everything like that. So actually, one of the main reasons that Grimsby caused so little disruption, despite being a much bigger eruption, was just because they changed the rules. It wasn't anything to do with the volcano at all. These models came in for a bit of criticism during the Grimsby eruption. There was more headlines, people saying in the Daily Mail, oh, the ash cloud's a myth and whatever. Well, actually, models are pretty good. They are really good at predicting where ash is going to fall, and they're pretty good at predicting when it's going to fall as well. So the diagram I've got here on the left is going to be a simulation that I ran for Grimsby showing where ash is falling at different times. And so you can see, as time goes, you can see the time at the top. The ash cloud comes round and it swoops across, and it comes across the top of the UK, just as we thought, and it does it during the 24th of May, just as we thought. So actually, the timing and location in these models is actually pretty good. What's harder to do is to predict the concentration. So the concentration means, to get the concentration, you need to have really good information about what's going on at the volcano. And that can be pretty hard to come by. And especially in the case of Grimsby, you saw the plume with the wind going in different directions at different heights and stuff like that. That makes it pretty difficult. In fact, in the Grimsby, the original estimates were a bit high, and they had to revise them downward. So things are improving, but they're definitely not fixed yet. There's still a lot of room for improvement. Okay, another reason why Grimsby was good, if we just keep clicking on, is that the weather was changing quite quickly. And so the ash that came was blown away quite fast. Whereas during Eyjafjallajökull, we just had a big high pressure and the ash sat on top of us all the time.